Good evening. This is Mrs. Boland with the University of West Florida, Elements of Statistics, STA 2023, Fall 2018. I'm continuing our lecture series on video for Mod 6 to assist the students who will be missing tomorrow's lecture due to Hurricane Michael. So here we go. We're picking up on our next video where we left off, working with the standard normal distribution. And our problem here says the graduate record exam, the GRE, is a test required for admission at many U.S. graduate schools. Student scores on the quantitative portion of the GRE follow a normal distribution with a mean of 150 and the standard deviation of 8.8. A graduate school requires that students score above 160 to be admitted. What portion of the GRE scores can be expected to be under 160? So let's go ahead and write down what we know. We know that we're normal distribution, which is important. That tells us we're going to be able to use the standard normal distribution to help us solve the probabilities. Mean is 150, so mu, let's see here, my computer's been running all day long. Mu is equal to, let me see if I can get that straightened out. Mu is equal to 150 right there. Our standard deviation is 8.8, so sigma is equal to 8.8. And graduate schools require above 160. So here we are at part A. What proportion of the combined GRE scores can be expected to be under 160? So for part A, we're asking what's the probability that X is less than 160? Really, we just want to rewrite this also as a Z, okay? So let's draw a picture of the question. The hotter my computer gets, the more temperamental it gets. So my picture, we're going to put mu in the center, which is 150. And we're going to draw right here 160. This is my X, so I'm going to plot my X on my normal curve, scroll up just a little bit, and then I'm going to shade the area of interest. And I'm interested in this area over here. So let's go ahead and make a standard normal curve. That's a mirror image of this picture here, where we're going to standardize our data values. And once we do that, we end up with our mean is 0. And we don't know yet what this value is. We have to standardize 160. Then we'll know what the z-score is, and that z value we'll put right here. So our formula for z is equal to x minus mu divided by sigma. So our x is 160. So it's 160 minus 150 divided by our standard deviation, 8.8. Grab your calculator out. This is going to be a fun lecture. I should not be doing this with a hot computer. Okay, so we're going to do 160 minus 150 divided by 8.8, and that is equal to 1.136. The 6 is going to round the 3 to a 4. So my z-score is 1.14. And then we're going to shade the area so it's just like the picture above it. We're going to shade the area of interest. And really what we have is we have that the probability that x is less than 160, because we've standardized this value right here, this is really the same thing as saying what's the probability that z is less than 1.14. Those are equivalent statements for this particular problem. So let's go ahead and go to our z tables and look up the value 1.14. Remember that our UWF z tables give the area to the curve of the left. So we're going to come over here where our positive z's are, and we're going to find z 1.14 is what we're looking for, not 41. Yep, 14. Let's try that again. If I can get my highlighter, there we go. So z 1.1, and now let's go over to the hundredths where it's 4. We're going to look at the intersection, and it's 0.8792. 0.8729 rather, 0.8729. So the area under the curve here is 0.8729. That's also right here, 0.8729. And so the probability that x is less than 160 is equal to the probability that z is less than 1.14, which is equal to 0.8729. Okay, and that is part A. So let's go ahead and scroll on up and look at part B. It says, what proportion of the combined GRE scores can be expected to be over 160? So part B, over 160. For B, we really don't have much math to do. What we need to remember is, in this case, it says, what's the probability that x is greater than 160? Well, we already standardized the value 160, didn't we? We found that the standardized value is 1.14. So this is going to be equal to, what's the probability that z is greater than 1.14? We already did the math, and we know that this part of the or this area under the curve is equal to 0.8729. Well, what is this whole curve, the area under the whole curve, equal to? The area under the whole curve is equal to 1.0, right? So this is going to be equal to 1.0, the whole curve, minus, if I subtract this area right here, which is 0.8729, 0.8729, that is actually going to be equal to this part right in here, which is the area that I'm now interested in. Don't you agree? So in that case, all I have to do is grab my calculator and say, what is 1 subtract 0.8729? And I find out that that is equal to 0.1271. So the area under the curve right here is 0.1271, 0.1271. And so if I were to add this value and this value together, I would end up with the entire area under the curve equaling 1.0, which is perfect. So what's the probability that I have an exam score greater than 160? Let's try that again, 0.1276. Let's look at part C. Part C says, what proportion of the combined GRE scores can be expected to be between 150 and 160? Okay, so part C says, what is the probability that we have a score between 155 and 160? 155 and 160. So 155 is less than x, which is less than 160. Okay, this is going to be equal to the probability, and we're going to be able to find some value on the left and some value on the right to bind to be boundaries for z. Okay, well, we've already calculated the 160, right? That's the 114. So we know the right-hand boundary. All we need to do now is find the left-hand boundary. So z is going to be equal to 155 minus 150. Is that our mean? Let's go back up. Yep, 150. Subtracting mu, divide it by the standard deviation, which is 8.8. And that is going to be equal to 155 minus 150 divided by 8.8, and that is equal to a positive 0.57. Just round off accordingly, okay? And so the probability that 155 is less than x, which is less than 160, is equal to the probability that 0.57 is less than z, which is less than 1.14. Okay, we already standardized this value earlier, and okay, the math's not going to change. And so let's go ahead and draw a picture of what we're looking for, though. We're looking for the area under the curve. If we have 150 here, and then we have 155. Let me go ahead and switch colors. Let me switch to pink on that. 155 and 160. The area of interest is right here between the two. That's what we're looking for. So let's go ahead and draw a standard curve that is equivalent to our first curve. The mean is going to be at 0. Now, my left z value is my 0.57. 0.57. My right value is going to be 1.14. And the area we're looking for is this area between those 2 points, okay? Now, how do we use our UWF z-tables to determine that? Well, when I look up in my tables, the 0.57, remember that the area that I'm provided is this area to the left, okay? So when I look up 0.57, I'm going to find this area over here. When I look up 1.14, I'm actually given this whole area all the way over, okay? Let me switch that to brown real quick. There's a brown. Let's see if that makes it a little bit more noticeable. Right here. There we go. So it's going to give me this whole area. So for me to find just the blue, I'm going to find the brown area, then I'm going to subtract the purple, and once I subtract off the purple, what do I have left? Just the blue, which is really what I need, okay? So let's go ahead and do that. So now I'm going to have the probability that 155 is less than x, which is less than 160, is equal to the probability that 0.57 is less than z, which is less than 1.14. And that is going to be equal to, so the probability that 0.57 is less than z, which is less than 1.14, is going to be equal to this area under the curve first in brown. That's the 1.14. We already looked that up, didn't we? That's the 0.8729. So we're just going to go ahead and grab that. So it's 0.8729. Okay, so this is 0.8729. And now we're going to subtract off the area under the curve for the 0.57. So let's come on down. Here's the area that we're going to be looking for. We're going to come in here for 0.5, and now we're going to come up here to the hundredths where it's at the 0.7. We're going to look at the intersection of the row and column, and we get 0.7157. 0.7157. So minus 0.7157 0.87. And we're going to throw that in our handy dandy calculator, and we're going to find that 0.8729 minus 0.7157 is equal to 0.1572. So the area under the curve here that's in blue is equal to 0.1572. And I can scroll this right here, and I can say right here this is equal to 0.1572. So going back up to C, and it says, what proportion of the combined GRE scores can be expected to be between 155 and 160? What proportion? It would be 15.72. So you see where it says the word proportion? You're going to want to put that in a percent, and so that's going to be 15.72%. And I think on part B, I just realized it said the same thing, and part A, what proportion, what proportion. So when you see proportion, go ahead and convert it to percent. So on part A, to answer the question for proportion, that should be 87.29%. And then for part B, when it said what proportion again, we need to convert our answer right here to be 12.71%. Okay? So if it says probability, you're going to leave it in decimal. If it says proportion, it's going to be percent. Now let's look at part D. What is the probability that a randomly selected student will score over 145 points? So part D says, what is the probability that a randomly selected student will score over 145 points? So we're going to scroll down below our tables. So we have some more blank notebook paper. And our question is, what is the probability that X will be greater than 145? That's really mathematically how you would write what's the probability that a student a randomly selected student scores over 145 points. You would say that X, because X represents the randomly selected student, and that their score is over 145. Now, let's write down a couple of things so we don't forget. That mu is 150, and sigma is equal to 8.8. Now let's go ahead and draw a picture. And our picture looks like this. Oh boy, my right-hand side of my monitor that I write on is kind of going out, I think, which is not a good thing. Okay, so we're going to put 150. Now we're going to put 145. 145 is below 150. You always put your numbers down here that represent X in the right numerical order. So we're negative infinity is over here and positive infinity is to the right. So make sure everything is in proper order. So we have 150. 145 is less than 150. So we're going to put 145 right here. And the question is what's the probability that X will be greater than 145? And so we're looking for, whoops, let me grab purple. I meant to grab, maybe this is purple, I can't tell. I don't know, we're just going to go with pink because that seems to be the only color I can pick up right now. Okay, so we're shading in over here the area of interest. Okay, now what we need to do is we need to go ahead and standardize this value. So we know that Z, whoops, that Z is equal to X, which is 145, minus our mean, which is 150, divided by the standard deviation, which is 8.8. And we throw this in our computer, or calculator rather, and we're going to find out that 145 subtract 150 divided by 8.8 is equal to negative 0.57. Okay, so negative 0.57. So let's go ahead and draw our standard normal curve. Remember, always draw your curves, especially on your exams, because I can find partial credit if you write things down. But if you don't write anything down, I can't find partial credit for you. I can't follow what you were doing. So I don't know where you made your mistake, and I don't know how much you know and what you don't know if you don't write anything down but an incorrect answer. So always give me as much as I can work off of, or writing as much down as you can on your exams. And pictures really help a lot. Okay, so here's our two pictures. This picture here represents our data, and this is our standardized data. Okay, so we're saying what's the probability that z is greater than, that z is greater than negative 0.57. Okay, so what's the probability that z is greater than negative 0.57? Well, let's go look that up in our tables. Remember, what part of the picture do our tables give us? They give us this part in here, which is not what we need. We need everything else, right? We know everything else underneath all of this, underneath the curve, is equal to 1.0. So if I have all of this under here equal to 1.0, and I subtract off the corner that I don't need, if I subtract this off, what am I left with? I'm left with everything in the pink, right? So I'm going to subtract off what is right in here, because that's what our tables give us. So let's go look at 0.57, a negative 0.57. Oops, I have to go up. So negative 0.57. So our third to the last row here is the 0.7. So let's come in here, 0.5, and then 1, 2, 3. So this would be our column, and it's 0.2843. 0.2843. So the area under the curve right here is 0.2843. 0.2843. So if I subtract from 1 the 0.2843, what do I get? I get 1 minus 0.2843. And that is going to not be what I put in there, because I ended up with a negative answer. And probabilities can never be negative. So that was a quick clue that I punched something in wrong. So this is going to be equal to 0.7157. So the area under the curve for this whole area is 0.7157. 0.7157, and that's this whole area in here. Let's go back up. This one was C or D. Let's look at this. Must have been D. And it says, what is the probability that a randomly selected student will score over 145? So it says probability. So we leave our answer in decimal form right here of 0.7157. Let's look at the next problem. Okay, looking at part E, it says, what is the probability that a randomly selected student will score less than 150 points? It says, do this one in your head. So think about it. What is our mean equal to? Our mean is equal to 150, correct? So if our mean is equal to 150, that means our z-score is 0. We know that the entire area under our curve is equal to what? 1.0. We know that it's symmetrical, so half of the area under the curve is on the left, half is on the right. So if we're looking for less than 150, that's on the mean, so that means 50% is on the left. or 0.5. So what is the probability that a randomly selected student will have less than 150? The answer is going to be 0.50. Then the last one. What is the percentile rank of a student who earns a quantitative GRE score of 142? So what percentile is the student in? So let's go down and look at that. So we scroll 142. So what percentile? So what percentile for score $142. Okay, we're going to start right here and we're going to standardize that value. We're going to put our mean in the center, 150. Okay, our value is right here, 142. Let's draw our standard normal curve. I need to know where this falls on my z tables, okay? So I need to know what the z is. So z is going to be equal to 142 minus 150 divided by 8.8, and that is going to be equal to negative 0.909, which makes that a 1. So negative 0.91. So what percentile? We need to come up with a number, okay, that we can say that X percent scored below this and X percent scored above it, okay? So that's where we're looking at for the percentile, okay? So we're going to look at negative 0.91 for our z-score in our tables. So negative 0.91. So negative 0.9 is right here. This is 0 and this is 1. So it's 0.1814. So 0.1814. 0.181814. I'm going to double check my memory. And that is correct. So it's 0.1814. And we go 1 minus 0.1814. And that is going to give me 0.8186. So what percentile are we in? We are in the 18th 0.14 percentile, okay? So we are in the 18.14 percentile, which means that 18.14% of the population made less than a 142, and 81.86% of the population made 142 or greater. Okay, so we're at the 18.14 percentile. Okay, here's our next problem. It says, the lifespan of a rechargeable battery is the time before the battery must be replaced because it no longer holds a charge. One tablet computer model has a battery with a lifespan that is normally distributed Oh boy, I thought I was in highlight mode. I'm not. There we go. That is normally distributed with a mean of 2.3 years and a standard deviation of 0.4 years. What is the probability that the battery will have to be replaced during the guaranteed period of 2 years? So the guaranteed period, the warranty, is 2 years. So the question is, what's the probability? So make sure we key in on the probability that the battery will have to be replaced within a 2-year period. We know that we're dealing with a normal distribution. We have the mean is equal to 2.3. We have a standard deviation of 0.4. 2.3 years, 4 years, and we have a guarantee of up to 2 years. So let's go ahead and draw a picture of what this looks like. What we're saying is (2.3) is our mean amount of time that the battery lasts. And it says, what's the probability that the battery will have to be replaced during the 2-year warranty? Well, the 2-year warranty is right here prior to the average length of the battery, which is good, really good. And so if a battery lasts less than 2 years, so that would be over in this area right in here, then we will have to replace the battery, okay? So right in here, if it comes in here, then we have to replace the battery. So what is the probability that X, a battery, will last less than 2 years? That's mathematically what we're looking at. And we want to go ahead and draw a picture of our standardized curve. So here's our standardized curve. 0 is our mean. We need to find out what is our Z value. So Z is going to be equal to 2 minus 2.3. 2.3 divided by our standard deviation of 4, or 0.4 rather. And we're going to throw that in our calculator, and we're going to find out that that is equal to 2 minus 2.3 divided by 0.4 is equal to negative 0.75. So our Z value right here is a negative 0.75. So when I say what's the probability that X is less than 2, that's the exact same thing as saying what is the probability that Z is less than negative 0.75. Don't forget your negative. That's rather very important right there, okay? Well, since our tables actually give us this area to the left, all we have to do is look that up. So let's go ahead and scroll down to our Z tables, and we're going to look for negative 0.7 is right here, and our 5 column is right there. So we're going to come down through here and look at the intersection, and it's going to be right there, 0.2266. So 0.2266. So this is equal to 0.2266. So 0.2266, and I like to put that in so we know what all of our numbers are and how everything is labeled. So the question is what's the probability that the battery will have to be replaced during the guaranteed period of 2 years? Probability is 0.2266, or approximately 20, if I can get that right, 23% of the batteries will have to be replaced in the warranty period. That's horrible. That's not a very good quality product, is it? If you're talking almost 25%, you're talking about almost 1/4 of the product needing to be covered because it's defective and does not last the warranty period. That's not good at all. Okay, here we go. Let's grab a different color ink here. Here we go. Magic Video Games, Inc. sells an expensive video game package. Because the package is so expensive, the company wants to advertise an impressive guarantee for the life expectancy of its computer control system. The guarantee period will refund the full purchase price if the company fails during the guaranteed period. The research department has done tests that shows that the mean life for the computer is 30 months, with a standard deviation of 4 months. The computer life is normally distributed, which is very important. How long can the guarantee period be if management does not want to refund the purchase price on more than 7% of the Magic Video packages? Okay, so management has said, I don't want to have to offer a refund more than 7% total, period. Find me that number, and then that's how we're going to determine what our warranty is going to be. So let's draw a really nice picture that represents what's going on here. So again, the Magic Video Games, Inc. sells an expensive video games package. Because the package is so expensive, the company wants to advertise an impressive guarantee for the life expectancy of its computer control system. The guarantee policy will refund the full package price if the computer fails during the guarantee period. The research department has done tests to show that the mean life for the computer is 30 months, with a standard deviation of 4 months. The computer life is normally distributed. How long can the guarantee period be if management does not want to refund the purchase price on more than 7% of the Magic Video packages? So here we go. We have our standard normal curve, because it said we are normally distributed. Where did we have that? Right there. Normally distributed. Okay, so we know we're on the standard normal. In the very center, maybe in the very center, we're going to take and put the mean, which is 30 months. Okay, so that tells us that mu is equal to 30. Our standard deviation is 4 months. So sigma is equal to 4 months. The computer is life is normally distributed, and how long can the guarantee period be if we do not want to refund a purchase price of more than 7%? So what this is telling me is in here is a value of 0.07, okay? And I need to find this number. I don't know what that number is. I'm going to put a warranty for X number of months. And if your machine breaks in that number of months, whatever that X is, I have to refund 100% the full price, okay, that you purchased the computer for. Management says we don't want to offer this more than 7% of the time. So this is the picture. So we want success to be 0.93, because 0.93 plus 0.07 is 1, right? So that accounts for 100% of the computer parts, or the computers that are packages that are published. So we want 93% of the people to never have to access their refund, okay, or to have a problem in this warranty time. So how do we find this? Well, let's think here. If we draw another picture and we make this one our standard normal curve, and the very center is what? Our mean, and our mean corresponds to 30. Right here, we could find a z, can't we? We can find a z such that the area under the curve to the left of it is 0.07. We have that ability. We can look at our tables and we can figure out what z is equal to, because our curve, or our tables, give us this part right here to the left. So let's go find our tables, and let's find a tail with only 0.07 underneath the tail. So we're going to scroll, and remember, I always call this the heart of your table. In here, this is the heart of your table, and this is where the area under the curve is provided. So we're kind of doing this in reverse, aren't we? Normally, we know the z and we find the probability or the area under the curve associated with a particular z value. In this case, we're not given the z. We're given the area under the curve, and we're told to find the z value. So the area under the curve is 0.07, and we need to find the z. So we're going to reverse search. So let's get a brightly colored highlighter here, and let's look for 0.07. Let's see here, 0.07. See, this is 0.01, 0.04, 0.06. Now 0.06 is getting close, right? So let's start looking for 0.07. Are we seeing anything in here? Nope, we're getting smaller. So let's come over here in 0.07. We have right here as an option, and whoops, I thought I had a highlighter. Let's see if we can get this as a highlighter. We have 0.078 and 0.0694. Now you're going to notice that this one right here is closer, because 0.0694 is closer to 0.07 than 0.0708. So the z value that we're going to use is going to be a negative 1.4. So negative 1.4, see that corresponds all the way over, and then going up to 8. So our z value is negative 1.48. A z value of negative 1.48 tells us that the area under the curve, our z value would be 1.48, negative 1.48. The area under the curve would be equal to 0.0694. We can't find the one that equals 0.07 exactly, and this we don't have an equal amount on each side of 0.07, so we're going to pick the number that corresponds, that is closest. So that's negative 1.48. So we're going to come back up here, and we say z, when it equals negative 1.48, okay, for a z value of negative 1.48, we have 7 or 0.07 underneath the curve. So let's look at our formula. We know that z, let me go ahead and switch colors actually. Z is equal to x minus mu divided by sigma. Let's plug in everything that we know to our formula. We know that we have a z, and that is negative 1.48 is equal to x. Well, we don't know what x is. That's what we're trying to solve for, just like in college algebra, right? We always had to solve for x. Minus our mean. Our mean is 30. Divided by, if I can get my division sign to right, our standard deviation, which is 4. So now, look, we have one equation, one unknown, standard algebra equation, solve for x. So the first thing we're going to do is multiply both sides through by 4, and then we're going to add x to both sides. So to solve for x, we're going to take negative 1.48, multiply that by 4, and we get negative 5.92 is equal to x minus 30. We will add 30 to both sides, and we get 24.08 is equal to x. So right up here, our x is going to be equal to 24.08. If we let x equal 24.08 months, okay, we would, statistically speaking, not have to refund more than 7% of the purchases, okay, because the batteries would not fail, okay. We'd only have a failure on 7% of the items that we sold. Reality, what would we let this be? We would say x is equal to 24 months. Okay, you're not going to go 24.08. You're never going to have a warranty like that, are you? It's going to be a full number. So the proper interpretation again is the company can guarantee that the Magic Video Games package should have a warranty of 24 months or 2 years. For this guarantee period, they expect to refund the purchase price of not more than 7% of the video game packages. Okay, example 9. Find the z-value such that 90% of the area under the standard normal curve lies between negative z and positive z. What this is asking us to do, I went ahead and I drew my standard normal curve. It's saying I need to find some unknown value z such that the negative of that z value and the positive of that z value, that 90%, okay, of the area will be under this curve. So 0.9% needs to be under this curve. So if I have 0.9% under this curve, that means that I have 0.45 on this side of the curve and 0.45 on this side of the curve. Okay? 0.45 on each side, because 0.45 plus 0.45 gives me my 90%. Now I know that on this half of my curve, okay, underneath my bell curve, on my standard normal, on the left-hand side, half of it is equal to what? 0.5. So if half is equal to 0.5, then that means the area under the curve that's left right here is going to be equal to 0.5 minus this area right in here, which is 0.45. That's a 4 there. And that is going to be equal to 0.05. Okay? So in each corner, I'm going to have 0.05 area under the curve. Now notice, I have 0.05 plus 0.45. That equals 0.5. On the right-hand side, I have 0.45 plus 0.045 or 0.5. Add those together, and that's 0.5. If I have 0.5 on this side and 0.5 on this side, I add them together and I get 0.1. Okay? So that accounts for 100% of the area under the curve. Now, what I don't know is my z-values, but I know the breakout underneath the curve. I know that my UWF tables give me the area under the curve right in here, correct? And so if I can find an area under the curve that is equal to 0.05, I can then back it out and find my z-value. Okay, so let's look at our z-tables here. Oops, I think they're right up here. Let me clear out our last exercise here. There we go. So we're going to be using our z-tables here to find an area under the curve that is equal to 0.05, because in the left-hand tail of my picture, I have 0.05, and I need to find what z-value corresponds. So I've been given the area under the curve, and I've been told the area under the curve in the heart of the table is where I'm going to look. The area under the curve is equal to 0.05. And so if the area under the curve equals 0.05, then I can back it out and find the z-value that corresponds to that area. So we're going to look, like right here, the area under the curve is equal to 0.0274. The area under the curve right here is 0.0505, and the area under the curve here is 0.0495. So the area that I'm looking for is right in here, because I'm looking for 0.05. Notice that 0.05 is smack dab in the middle of these two values. When it is smack dab in the middle of the two values, then and only then do you go ahead and split the difference. So my z value for this is negative 1.6. Okay, so negative 1.6. Negative 1.6. Now I need to figure out the 100th value. Okay, let's look here at the 100th values. It could either be 0.4 or, I'm sorry, 0.04 or 0.05. Well, if we look at the difference between the two, then that's going to give me 0.645. I don't get a 4 from here and the 5 from here. That's not how that works. I'm actually taking the difference, I'm splitting the difference between the two. I'm looking at the middle value between those two, and that's how I get the 4, 5, okay? I'm going out to the 1,000th unit to split the difference. So my z value is negative 1.645. So that means right here I get a negative 1.645, and over here I get a positive 1.645. So what is my z value such that 90% of the area under the standard normal curve lies between negative z and positive z? My z value is 1.645. Okay, here is our next problem. It says find a z value such that 3% of the area under the standard normal curve lies to the right of z. So find a z value, so we're looking for a z value, such that 3% of the area under the curve, or under the standard normal curve, lies to the right of z. So the right is very important. Let's draw a picture that represents the question. We're talking about the standard normal curve. Our mean goes in the center. We need to find some z value such that the area to the right is only 3%, 0.03. Now 0.03 is smaller than 0.5, so that tells me it's going to be a positive z value. So my z value is going to go on the right hand side because it also says the area has to be, to the right has to be the 0.03, and I'm looking for a z value. So to find a z value where the area to the right is 0.03, well, if the whole area of the curve is equal to 1, and I'm going to then subtract off 0.03, what's left? Whoops, 0.97. So this whole area in here is equal to 0.97. Now my tables that we have give us the area to the left over here. Okay, that's what my tables give me. It gives me all of this area over here to the left. So all I need is my z value. So I'm going to look at my tables and I'm going to find it where I have a z value that corresponds where the area to the left of my z value is 0.97. As long as the area to my left equals 0.97, then I know the area to the right is 0.03, which is what I was told to find. So let's go look at our z tables for 0.97. So it's going to be somewhere in here, 0.97, 0.97. This number right here is very close. You can't get much closer to 0.97. Okay, so it's going to be 1.8, and when you go up, 8. Okay, so it's 1.88 is the z value, 1.88. That corresponds, there we go, so you can see both. 1.88 is the z value that corresponds where we have 0.9699, which is equivalent, as close as we can get, to 0.97. Okay, so we're going to look at a z value then of, oops, not that one. Here we go, right in here, there we go, of 1.88. 1.8. So what z value corresponds to an area under the curve equal to 0.03? Z is equal to 1.88, and that is our answer. Okay, here's another problem. It says, let's extend the last exercise. We're going to build off of what we just did. It says, suppose that the time to complete a test is normally distributed with mu equal to 40 minutes and sigma equal to 5 minutes. After how many minutes can we expect all but 3% of the test to be completed? So let's draw a picture of that. So what we're saying is we have a distribution of test times. They're normally distributed. Okay, they're normally distributed. Mu is 40. And we want to know after how many minutes can we expect all but 3% of the test to be completed. So what I want to find here is I need to find some value of x, which is going to represent time, which we don't know what that is going to be yet, such that all but 3% of the exams are completed. So 97% of the exams are completed, 3% are not. Well, that's exactly what we just did a moment ago, isn't it? So let's draw our standard normal to match our current question. So our mean goes in the center. When we looked this up before, we found that we were going to have a z of 1.88, and when we had 1.88, that told me that I had 3% still underneath the curve here, or 0.03 underneath the curve there, and this area underneath the curve was 0.97. So that 97% of the students will have completed the exam, but 3% will not have completed the exam. That's what this picture represents. And I'm just going to scroll up to remind you that we did find that it was 1.88. So this is the problem that we're in reference to. So pause the video if you need to look at it a little bit longer. So again, I know that I have z is equal to x minus mu divided by sigma. I know what my z is equal to. My z is equal to 1.88. I don't know what my x is. That's what I'm solving for. Minus my mu, which is 40, divided by my standard deviation, which was given in the problem as 5. Mathematically speaking, there is our problem, okay? So now what we need to do is use algebra and solve for x. So we'll multiply both sides through by 5, so we'll get 1.88 multiplied by 5 is equal to x minus 40. We'll add 40 to both sides. We'll try to add 40 to both sides if my pen will work. Scroll up just a little bit. And we end up with 1.88 multiplied by 5 plus 40 is equal to x. And when you throw this in your calculator, you're going to find out then that, well, if I can write, x is equal to, you can tell my computer screen is giving me some fits there. Sorry about that. Is equal to 49.4 minutes. Okay? So 49.4 minutes. And so x is going to be equal to 49.4. Okay, and that is how we finished that particular problem up. Okay, now we're going to start talking about the central limit theorem. The central limit theorem is very foundational for statistics. It's a very, very important theorem that gives us a lot of power and a lot of ability to do inferences that otherwise we would not have the opportunity to do. The central limit theorem tells us that if we have x and it's a random variable with a normal distribution, again, very key, we have to have that normal distribution with a mean mu and a standard deviation of sigma, that x bar, there's an x bar right there, will be the sample mean corresponding to the random variable of size n, taken from the x distribution. Concerning x bar, then the following are true. The distribution of x bar is normal. The mean of the said distribution is equal to mu, and the standard deviation of the said distribution is the standard deviation divided by the square root of n. So the sigma divided by the square root of n. These are very important, okay? We must remember those and we must know how to use those. So what this means is if x has a normal distribution, we know that x bar will be normally distributed for any sample size n, okay? What this means is what we've been talking about up to this point is an individual. If I said I wanted to know, if I said Johnny's last game, I'm sorry, not Johnny's last game, Johnny's average of bowling is 100, okay, and his standard deviation is 5. What's the probability of Johnny scoring 110 on his next game? That's one person, one game. That's what we've been talking about. An individual, one observation, one probability. Okay? Now what we're doing is we're expanding this to be an average. Okay? We're looking at the mean. And instead of saying, what's the probability on Johnny's next game of him getting 110? I'm changing the question to say that maybe Johnny bowls 30 times a year, okay? And I would be saying that what's the probability that Johnny's average next year or the next season will be 110? So instead of looking at just one game of Johnny's, we're looking at his whole season. And I want to know what's the probability that his average has is over 110. So he's going to have 30 games. We're going to have to average all those 30 games together. And I want to know what the probability of that actual average of his 30 games being over 110. So that's where we're going with the central limit theorem. The central limit theorem, I want to expand on this concept a little bit more, okay? And if I was in class with you right now, we would actually do a little survey, and tomorrow we will do a survey in class where we will take approximately 10 to 15 students from the front rows, and then 10 to 15 students from the middle rows, and then 10 to 15 students from the back rows. And I would ask everybody their age. And what we're going to find out is that the average age of everybody in class typically is somewhat close, okay? And so that if I said I was going to let n in our class equal let's just say 10, okay? If I were to say that n is equal to 10 and we have 90 students, all 90 students were to show up, okay, so our population then is 90, I could choose 10 students out of that 90, many different combinations, right? I could choose the first 10 that sit in the first row. I could choose the second row, the first 10 people in the second row. I could look at the third row and I could choose the first 10 people in the third row. I could look at the fourth row and I could choose the first 10 people on the fourth row. I could look at the fifth row and I could choose the first 10 people on the fifth row. And every one of those averages would be different, okay? They would be close, but they would be uniquely different. Or I could say I could take 5 students on the first row of the left side of the room and 5 students from the right side of the room on the front row. I could calculate X bar using that, right? Or I could calculate the average of the 10 students looking at the second row and choosing 5 students on the left side of the second row and 5 students on the right side of the second row. I could do that all the way back, and I would again end up with different averages, age averages. I would still be having a sample size of 10. They would all be chosen from the population of my 90 students in my statistics class, but the averages would calculate out differently. I could say I'm going to choose 5 students on the far left-hand edge of my classroom and 5 students on the far right-hand edge. And then I could go in 1 seat for the next sample. Point being is I can mix my samples up a whole bunch of different ways, always taking 10 students to calculate the average, and I would get a different average every time. What happens though if I started to plot my X bars, my averages, okay, I'm calculating all these different averages of these 10 students and their ages in my statistics class. If I started to plot the actual means, okay, not the individual student ages, but the different sample means, those sample means, hopefully that'll pick up and follow on. Of course it will not. The sample means will take on a normal distribution if the population that I'm pulling it from is a normal distribution. Okay? So my X bars that I'm plotting, if I'm pulling from a normal distribution, those X bars will also, when I plot all the different ways that I can calculate those sample means, they will also take on a normal distribution. What we also find is that the larger the sample size gets, okay, typically we would say is greater than or equal to 30, okay? So as long as my lowercase n is greater than equal to 30, it actually doesn't even matter what the distribution is of the raw data. That the X bars, as long as the sample size is greater than 30 or equal to 30, the distribution of my means will take on a normal distribution. This is extremely powerful because now I can predict what might happen in the future based on past data if my sample sizes are large enough, or if I know for a fact that I'm dealing with a normal distribution. Okay, I want to know what the average might be of something. So let's go ahead and move forward with this concept and do some application. Okay, suppose a team of biologists has been, Suppose a team of biologists has been studying the Pinedale Children's Fishing Pond. Let X represent the length of a single trout. This is very important that this is of a single trout. Taken at random from the pond. This group of biologists has determined that X has a normal distribution, so we're dealing with a normal distribution, with a mean of 10.2 inches and a standard deviation of 1.4 inches. What is the probability that a single trout taken from random at the pond is between 8 and 12 inches long? Okay, this is just like what we've been working on all day long. So we're saying that mu is equal to 10.2 inches. And we have sigma is equal to 1.4 inches. We're asking, what is the probability that 8 is less than X, which is less than 12? What's the probability that a single trout taken at random from the pond is between 8 and 12 inches long? That we catch a trout and it's between 8 and 12 inches long. That's the question. Well, we need to standardize both of those values, right? We need to find out what the Z is. So let's go ahead and just draw a picture. We're saying that our mean is 10.2 inches and we're looking for 8 to 12 to be our boundary. So 8 is less than 10, right? So we're going to put 8 on the left. 12 is greater than 10, so we're going to put 12 on the right. And the area that we're looking for is this area right in here between those two values. In order to solve this, I must standardize each of these values and find the area under the curve that is associated with the standardized values. So in the center is going to be our mean. Now I need to find my negative z and my positive z. My negative z will correspond with my 8. My positive z will correspond with my 12. So z is equal to 8 subtract 10.2 divided by 1.4. We're going to throw that on our calculator. And I have 8 minus 10.2 divided by 1.4. And that is equal to a negative 1.57. So my z here is negative 1.57. And then my other z, because I have to standardize my 12, is going to be 12 minus 10.2 divided by 1.4. We're going to throw that in our calculator, and I end up with 12 minus 10.2 divided by 1.4, and that is equal to a positive 1.29. So over here, 1.29. And so right here, I'm going to highlight the area of interest so that my pictures represent each other properly. Okay, so I'm looking for that area right there. Again, an equivalent statement to what is the probability that 8 is less than z, which is less than 12, an equivalent statement would be, what is the probability that negative 1.57 is less than z, which is less than 1.29? Exact same question, okay? So to find this out using our tables, again, our tables are going to give us all the way out to negative infinity. So we're going to look first at the probability that z is less than 1.29. We're going to get this area to the left. So let's look up 1.29. Okay, here we are. Remember, our picture shows us the area that the tables are going to give under the curve. And so we're looking for 1.29. So 1.2, and then 9 is over here. We're going to look at the intersection of those two. So I have 0.9015, 90, 15. So 0.9015 is going to be right through here. So the probability that z is less than 1.29 is equal to 0.9015. Okay, so I'm going to put 0.9015 right here, and that is the entire area. Oops, let me get brown is what I was trying to grab. There we go. So that is this whole area right through there. Okay, and that is equal to 0.9015. Okay, so all the way out down to negative infinity. Now I need to take and look for the area in the curve right here past negative 1.57 and subtract this part off. Okay, and then that difference is going to give me what's left in the pink. Okay, so let's look at the negative 1.57 next. So we're going to look under negative 1.5 and then 7. And the intersection of those two is right there, which is 0.0582. 0.0582. So in this area right in here is going to be 0.0582. So we're saying that the probability that z is less than negative 1.57 is equal to 0.0582. So I'm going to subtract that off from up here, 0.0582, and I'm going to find out that the difference then is equal to, we go 0.9015, subtract 0.0582. Oops, got to turn on that calculator. I guess it's been off for a little while. So 0.9015, subtract 0.0582, and that is equal to 0.8433. So 0.8433. So for part A, it says, what's the probability that a single trout taken at random from the pond is between 8 and 12 inches long? The probability is 0.8433. That is the probability. So right in here, 0.8433. That's the area between 8 and 12. Okay, we found this area right here all the way to negative infinity is 0.9015, and then we found that the area from this point all the way out to negative infinity is the 0.0582. So we deducted from this whole thing this little bit right here, and it left the remainder in the pink area, which is the 0.8423, or 33 rather. Alrighty, let's look at part B. It says, what is the probability that the mean length, okay, the mean length of 5 trouts taken at random is between 8 and 12 inches long? Now notice, on the very first one here, it says a single trout, just one trout. Now we're looking at 5 trouts. We're going to average the 5 trouts' lengths. We're going to go fishing. We're going to catch 5 trouts. We're going to measure them. And then we're going to average the 5 measurements together. I want to know what's the probability that the average that I just calculated from those 5 random trouts, that the average is between 8 and 12 inches long. Okay, it's a totally different question than one single one. This is where the central limit theorem comes in, because now I have 5 trouts I'm catching. I'm going to take and measure each of the 5, and then I'm going to average the length. And I want to know what is the probability that the average of the 5 trouts is between 8 and 12 inches long. Okay, so now we have different formulas to use. So let's go ahead and look at what we have here. We have a new z way of calculating z. We have a z-score that is going to be equal to x minus mu, okay? But it's x bar minus mu. Our other one was x minus mu. Our item of interest now is not what's the probability of x, it's the probability that x bar will be a certain value. So we're standardizing our x bar, our mean, okay, from the sample. So this is a sample mean. We're going to subtract off the population mean. We're going to divide it through by sigma divided by the square root of n. So our old z formula was just a plain x. That x is now changed to the sample mean, subtracting off the mean, and then our old one was divided through just by the standard deviation. Now we're dividing through by the standard error about the mean, which is our standard deviation divided by the square root of n. You'll notice that I put parentheses right here. It's very, very, very important that when you use your calculator, you put your parentheses here and you put your parentheses here. If not, you will not get the correct answer. Please make sure you use your parentheses. You know, I tell you in class, overuse parentheses. It's better to use too many parentheses to make sure that your order of operation is being done properly than to use too few and to have your order of operation goofed and then getting the wrong answers. So let's review here. In this case, we're asked, what is the probability that 8 is less than x bar, which is less than 12? Okay. We were given that our mean is equal to 10.2 and our standard deviation is equal to 1.4. Oops. We were also given that our sample size, how many fish did we catch before we calculated our average? We caught 5 of those fish. Okay, so we were told that our sample size is 5. Now we have everything that we need. We're going to use for our x bar our 8 and our 12. Okay, because our x bar goes there. We have our mean right over here. We have our standard deviation right here. We have our sample size right here. So our picture is very similar to what the other one was. We put our mean in the center of 10.2. We're going to put our x bars, our sample means. We want to know what's the probability that a sample mean of our 5 fish will equal between 8 and 12. That's our sample mean. We're going to shade in the area of interest. Now let's create our standardized picture. Scoot up just a little bit. There we go. Put our mean in the center. And now I need to calculate my z-values. My z-values are not going to be the same as they were in the last one, because the last one had to do with a single trout, an individual trout. Now we're dealing with the average of 5 trouts. So our formula has changed. So our z-values will change. So if I want to find what is the probability of our z's with x bar equaling 8, we're going to have z is going to be equal to x bar minus mu. So 10.2 divided by our standard deviation, 1.4, divided by the square root of 5. Now make sure you remember your parentheses. Everybody, pause the video if you need to. Go grab your calculator, and before you see me put the answer up here, calculate it yourself to make sure you have your order of operation correct. Okay, so pause the video for just a second until you have grabbed your calculator and you are personally calculating this number. Okay. So if you punch this in just like this, you will get negative 3.51. Because it's a z-value, you don't need to go past 2 decimal places. Now, if you went ahead and just calculated this to begin with, and let's say you only rounded it to 2 decimal places, your answer is going to be different than mine slightly, okay? I prefer that you not calculate this independently and just use 2 or 3 decimal places. I prefer that you go ahead and put it in your calculator in full form and let the calculations run to get a more accurate answer. Okay, so on the left-hand side, we have negative 3.51, and now let's calculate our other z. So z is going to be equal to 12 minus 10.2 divided by 1.4 divided by the square root of 5. Again, punch this in your calculator. It's going to be parentheses, 12 minus 10.2, close parentheses. Hit your divide, open parentheses, 1.4, divide, do your square root, 5, close your parentheses, and equal. And that is 2.87. Now, if you're using the TI-30, the verbal steps that I'm giving you will be different. If you're not able to figure it out on your own, just see me after class or raise your hand during class and I will help you. Alrighty. So this is going to be 2.87. Okay, now these z values are totally different than what we just had, right? So let's go ahead and finish this out. So this is going to be equal to the probability that negative 3.51 is less than z, which is less than 2.87. Now, this is going to be equal to, what's the area under the curve from 2.87 all the way out to negative infinity? Well, let's look it up. 2.87 is going to be somewhere in here. So got to go even further. 2.8, and then 7 is right here. So 7 is right there. So that's 0.9979. So 0.9979. So the probability, So the probability that z is less than 2.87 is going to be equal to 0.9979. Okay, so that's from here all the way out to negative infinity, okay? And that's 0.9979. So we're going to write that right here, 0.9979. And we're going to subtract off this part in here. Because if I have it from here all the way out to negative infinity, and then I subtract off this part here, what do I have left? Just this part right here. So the next thing I need to know is, what is the probability that z is less than negative 3.51? Okay, so let's scroll over and look at negative 3.51. Negative 3.51. We don't actually have a negative 3.5. I think on here it tells you how to deal with that. Yes, it says for values less than 3.49, use 0. Okay, so we're going to approximate then at this as being 0.00. So we would actually subtract. I'm going to just write it here so that you can see that. And so our answer is going to be 9979. Okay, so what is the probability that we catch 5 trouts in this pond? We average the length of the 5 trouts, and we find that the average length of those 5 trouts is between 8 and 12 inches long. The probability of that happening is 0.9979. Very strong probability, right? Almost 100% probability of that event happening. Contrast that with our other one of only being 84.8433. Okay, a single fish that is between 8 and 12 inches long, we only have 0.8433 probability of catching a fish between 8 and 12 inches long. Okay, we have a 0.9979 probability of catching 5 fish and having the average length of those 5 fish between 8 and 12 inches long. Do you see the difference? I hope that you do. Okay, let's do some more application. So if you're a little fuzzy, it'll help cement it in. Okay, let's go ahead and discuss the central limit theorem a little bit more. Okay, remember I said before that the central limit theorem can actually be applied for any distribution. So if x, the random variable, follows any distribution, not just the normal distribution, but we have a mean mu and the standard deviation sigma, then the sample mean based on the random sample size of n will have a distribution that approaches the distribution of a normal random variable with a mean of mu and a standard deviation of sigma divided by the square root of n as n increases without limit. This generalization tells us that x can take on any distribution whatsoever, but as the sample size increases, the distribution of x bar, or the mean, is approximately normal. And the larger your sample size is, the better. How can we apply the central limit theorem? This is known as the central limit theorem, so that we can convert the distribution of x bar to the standard normal. First, n must be greater to or equal than 30. Very important. If your sample size is less than 30, we must know that we're dealing with data from a normal distribution. If we do not know, and we cannot assume, it's not valid for us to assume that the data that we're dealing with comes from a normal distribution, we cannot use the central limit theorem. It's plain and simple. You cannot do it. We have other techniques, other statistical techniques. It's just beyond the scope of this particular course. So don't worry about it. There are techniques, and if you go ahead and further your studies in statistics, you'll discover what those are. But for this course, we must be able to assume that the data is coming from a normal distribution if the sample size is less than 30. If the sample size is 30 or greater, then it doesn't matter what the distribution is that the data is coming from. Because of the central limit theorem, we know that the mean, the distribution of x with a standard deviation, will take on a normal distribution, okay? And that's all because of the central limit theorem. But again, mu is the mean of the distribution. X is the standard, sigma is the standard deviation of x, of the x distribution, and n must be greater or equal to 30, okay, for us to be able to apply the central limit theorem, which means we can assume normality, okay? When we have that, our mean sub x bar is just going to be equal to our population mean, okay? Our standard deviation about x bar is going to be equal to the standard deviation divided by the square root of n. Our z is going to be x bar minus the mu about the mean divided by the standard deviation about the mean, which is also equal to x bar subtract the mean divided by the standard deviation divided by the square root of n. Okay, so we're going to practice this some more. It says here, a certain strain of bacteria occurs in all raw milk. Let X be the bacteria count per milliliter of milk. The health department has found that if the milk is not contaminated, then X has a distribution that is more or less mound shape and symmetrical. What does this mean? Mound shape and symmetrical. Well, that tells you it basically has a normal distribution, right? Okay. The mean of X, of the X distribution, is equal to 2,500. The standard deviation is equal to 300. In a large commercial dairy, the health inspector takes 42 random samples. What does that tell us? That tells us that little n is equal to 42. Our sample size is equal to 42. So he takes 42 random samples of milk produced each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain a sample mean bacteria count called X bar. Part A. Assuming that the milk is not contaminated, what is the distribution of X bar? Well, remember just a moment ago, we said that, excuse me, that mu sub x bar is equal to mu, right? And so in this case, we were given that mu is equal to 2,500. So that is for part A. Part B says, assuming that the milk is not contaminated, what is the probability that the average bacteria count, X bar, for one day is between 2,350 and 2,650 bacteria per milliliter? Now, this asked for one day, right? What's the probability that our average of the 42 samples taken that one day are bound between 2,350 and 2,650? So that means I'm going to write down here that mu is equal to 2,500. Sigma is equal to 300. And N is equal to 42. Okay, so I'm going to scroll up a little bit because I don't have enough room to work, okay? And so for part B, it says, what's the probability that our X bar is between 350 is less than X bar, which is less than 2,650. That's the question, okay? So we need to standardize both of these. I'm going to scroll up a little bit more. Let's go ahead and draw a picture of what we're looking at. We're going to say, what's the probability? Our mean is 2,500. 2,500. 2,350 is below 2,500. So to the left, we're going to put 2,350. And then 2,650 is greater than our average. So to the right, we're going to put 2,650. And it said, what's the probability that the average bacteria count is between those values? So we're looking for this area right here. Okay, so that's the area under the curve that we're looking for. So first things we have to do is we have to standardize each of these values. Because we can apply the central limit theorem, we're going to standardize each of the means. The formula to standardize the mean is going to be it is X bar minus mu divided by sigma divided by the square root of n. Okay, so that's our formula. So X bar is 2,350 minus mu, 2,500, divided by 300, divided by the square root of 42. Grab your calculators. Punch this in on your own to make sure you know how to use your calculator. This is a good time for you to learn how to use your calculator. And some of you are sitting there saying, Mrs. Boland, really? This is a simple division. Why do I need to take and practice using my calculator? Just trust me, okay? Just trust me. Okay, so I ended up with negative 3.24. Now we're going to standardize the next value. Okay, we're going to scroll up just a little bit. And we have z is equal to, it's going to be 2,650 minus 2,500 divided by 300 divided by the square root of 42. And we're going to put this in our calculator. Don't forget your leading parentheses here, okay? So we have 2,650 minus 2,500 divided by 300 divided by the square root of 42 And I end up with a positive 3.24. Let's go ahead and draw our standard curve. That is a mirror image of the curve with our data. And it's going to look like this. And on the left-hand side, we're going to have negative 3.24. On our right-hand side, we're going to have a positive 3.24. And we're going to highlight okay. I'm going to continue with the same pattern solving this. There are a couple of other options. I'm not going to demonstrate them because I don't want to confuse people who aren't recognizing them. However, if you see a couple of other options that might be a little quicker and a shortcut, and you end up with the same answer I do, chances are you figured it out and you're not making a mistake and you're not doing something wrong, okay? It's fine to use any shortcuts that you recognize and that you see, okay? So, with that said, let's move on. So, this is going to be equal to, right here, the probability that negative 3.24 is less than z, which is less than a positive 3.24. Okay? And so I'm going to calculate this area, and then I'm going to subtract this area, and the difference is going to give me the pink area that I'm interested in. So let's look up what is the probability that z is less than 3.24. That is going to be equal to, oops, evidently, let me pause. I didn't put that printout in. Okay, now I have my printout. So let's look 3.24. So we're going to scroll on down until we find 3.2, and now we have to go to 4. So this is 0, 1, 2, 3, 4. So again, 0, 1, 2, 3, 4. So the answer is 0.9994. So we're going to come up here, we're going to put 0.9994, and that is this whole area all the way over here, right? So 0.9994. So we're going to put this as equal to 0.9994. Oops, not equal to, but we're going to subtract off this area right in here, which is going to be the probability that z is less than negative 3.24. So we're going to look up this area here, negative 3.24, negative 3.24. So right there is 0.0006. So 0.0006. So I know that from here all the way out to negative infinity is the 0.9994. I know that this area right in here is 0.0006. So if I subtract this off of the part that goes all the way out to negative infinity, I'm left with just the part in the pink. So minus 0.0006, that difference is 0.9994 minus 0.0006, and that is equal to 0.9988, right there. So what is the probability that I am taking a random sample today of 42 samples of milk, and at the end of the day I average those 42 samples together, and my X bar, my average bacteria count for the day, is between 2,350 and 2,650, it's 0.9988, almost 100%. So very, very high. So let's think about this a little bit critically. The probability that the average bacteria count is between 2,350 and 2,650 is obviously very, very high. If we observe X bar is less than 2,350, so lower bound, we may suspect that there are chemicals added to reduce the bacteria count. On the other hand, if we observe that X bar is greater than 2,650, we may suspect that there's another type of biological contaminant that caused the bacteria count to increase, or also a herd infection. Okay? So here we go. We've got one example left, and then we're done for the day. Okay, here's our last problem for the day. In mountain country, major highways sometimes use tunnels instead of long, winding roads over high passes. However, too many vehicles in a tunnel at the same time can cause a hazardous situation. Traffic engineers are studying a long tunnel in Colorado. If X represents the time for a vehicle to go through the tunnel, it is known that the X distribution has a mean of 12.1 minutes and a standard deviation of 3.8 minutes under ordinary traffic conditions. From a histogram of X values, it was found that the X distribution is mound shape with some symmetry about the mean, aka we can assume that the data came from a normal distribution. Very important. Engineers have calculated that on average, vehicles should spend from 11 to 13 minutes in a tunnel. If the tunnel time is less than 11 minutes, traffic is moving too fast for safe travel in the tunnel. If the time is more than 13 minutes, there is a problem of bad air quality, too much carbon monoxide, and other pollutants inside the tunnel. Under ordinary conditions, there are about 50 vehicles in the tunnel at one time. What is the probability that the mean time for 50 vehicles in a tunnel will be from 11 to 13 minutes long? Okay, let's gather our data here. We're given that mu is equal to 12.1 minutes. Our standard deviation is equal to 3.8 minutes. Our sample size is going to be 50. And we're being asked to find what is the probability that that 11 is less than X bar, which is less than 13. Okay? So this is X bar. I want to make sure you can see that that's an X bar. X bar. There we go. Now let's draw a picture to represent the problem that we're solving. We're going to draw our standard normal. We're putting X bar in the center. X bar is 12.1. We're looking for the probability that 11 is less than, or X bar is less than 11, or I'm sorry, greater than 11. It's getting late, guys. I'm getting very tired. And that X bar is less than 13, so that it's bound between these two values right here. Okay? That's what our picture looks like. Let's standardize these values. So we're going to end up with Z is equal to 11 minus our average, our mean of 12.1 divided by our standard deviation, 3.8 divided by the square root of our sample size, which is 50. And we're going to throw that in our calculator, and we're going to find out that this is equal to 11 minus 12.1 divided by parentheses 3.8 divided by the square root of 50, and that is going to be equal to negative 2.04, negative 2, whoops, 2.04. So let's go ahead and start our standard normal curve. And it's going to look something like this. Where on the left-hand side we have negative 2.04. I now need to calculate my right-hand z, where I'm standardizing 13. So I get z is equal to 13 minus 12.1 divided by 3.8 divided by the square root of 50. And I'm going to throw this in my calculator, and I'm going to have 13 minus 12.1 divided by 3.8 divided by the square root of 50. Again, guys, make sure you're putting this in your calculator so you're verifying that you know how to use your calculator correctly. And we get a positive 1.67. Oops, I thought I changed that color. Positive 1.67. And so we're looking for the area under the curve here, and we're saying, what is the probability that I randomly select 50 cars that are going through the tunnel, and that the average time that it takes for those 50 cars to go through the tunnel is between 11 and 13 minutes long? That's really the question that's being asked. So this is the exact same thing as saying, what is the probability that negative 2.04 is less than z, which is less than 1.67. This is the same thing as saying, what's the probability of negative 2, what's the probability of 1.67 I'm very tired. I guess I'll have to edit that part out. This is the same thing as what's the probability that z is less than 1.67, subtract the probability that z is less than negative 2.04. So I'm saying the probability that z is less than 1.67 minus the probability that z is less than negative 2.04, and that is going to be equal to, let's look up this probability first, 1.67. Oops, I guess I have to go up for that. 1.67, 1.67, we're going to intersect right there, is going to be 0.9525, 0.9525, 0.99525, subtract the probability that z is less than negative 2.05. So let's go find negative 2.05. So negative 2.05, or I thought it was a 4. I'm really tired. Negative 2.04. There we go. I told you I'm getting tired. So 2.04 right here. There we go. 0.0207. 0207. 0207. 0207. And this is going to be equal to, for this in our calculator, and we have 0.9525 minus 0.0207, and that is going to be equal to 0.9318. Okay, so what is the probability that 50 cars going through the tunnel, that the average length of time that it takes the 50 cars to go through the tunnel is between 11 and 13 minutes long? The probability of the average time being between 11 and 13 minutes long is 0.9318. So, interpretation is it seems about 93% of the time there should be no safety hazard for the average traffic flow. Okay, gang, this should be a good solid start on normality for you. in the central limit theorem. Watch the videos as many times as you need to. If you need me to help you solve some other homework problems, to give you more examples, let me know and I will see about doing that. Have a good night. I hope everybody was safe during the hurricane. Take your time coming back, and I probably will see most of you next week on Tuesday. Take care and good night.